Welcome everybody to this week's Geotalk Online. Thank you for joining us from wherever you are, and of course thank you to John Hancox from CCIC Coal for the sponsorship of these Geotalks. No virtual drinks and chips, but the Geotalks are sponsored by John Hancox. And also to remind you that if you've missed any Geotalks recently, you can watch them online on our YouTube channel, Wits Geosciences on YouTube. Not all of the talks are there, of course, because some presenters don't want their talks to be posted for all of eternity on YouTube, but many of the talks that you may have missed will be on YouTube. So today we welcome who is becoming a very regular Geotalk speaker, for which we are very grateful, and that is Dr. Glen Nwaila, who is a staff member here in Wits Geosciences and part of our team of economic geologists. And as you'll see today, he brings a very unique view and aspect to economic geology research in the school. So it's a great pleasure to have Glen here. For those of you who don't know Glen or haven't attended his previous talks, Glen did his undergrad and postgrad education between UJ, UCT, and Würzburg University in Germany, and has worked extensively in the gold industries in South Africa. He's also worked in the consulting industries for Deloitte, and is now working for the school very closely with Chimera and our Agri team. So Glen, welcome. Thank you very much. To remind the audience, you can ask questions at any time in the Q&A panel that you see on the right-hand side of your screen, and Glen will handle those questions at the end. So thank you for joining us from wherever you are in the world, and I'm going to ask Glen to share his screen and unmute. Okay, Glen, I can see your screen, and I'm just going to get your video up there. All right, Glen, you are in 2 seconds, you are live, and we have an audience of about 30 people, so thank you all for joining us. And over to you, Glen. Go for it.
Thank you, Grant. Hi, everyone. Thank you for joining us for today's Geotalk. The topic that I will be presenting covers a range of disciplines, but to preserve a uniform narrative, I'll keep it at a level that we can all relate to, which is mainly on the field of applied geosciences. So the title of my talk, as you can see, is different to some of the talks that I have given before, and is titled Computational Modeling of Ore and Petroleum Systems using Machine Learning and Sequential Gaussian Simulation. Note that some of the sections of this presentation may be confusing or complex to understand for those who are not familiar with this discipline, but I will do my best to ensure that all the useful or key points are conveyed clearly. So I will first give you a bit of a history, which many of you may be familiar with it. And this is that the discipline of geology can be categorized into two main categories. The first one is geotheory. The other one is geologic. And in geotheory, we're mainly concerned with the fundamentals and the principles governing the field itself, whereas in the geologic, we mainly focus on the reasoning, logic, and interpretation. So this did not happen by any accident of any kind, but it was a journey that took over 220 years of knowledge evolution. So when this field started, a geoscientist only had to deal with logic in science, as you can see, around 1812, and very few concepts because it was still in its early stages. So logic in science was introduced around the early 1800s, followed by understanding of the rock cycle around the 1830s. And then this is where we often hear of the people speaking of the fathers of geology. Following this era of building a foundation of geology as a discipline, additional concepts such as sedimentology and plate tectonics were introduced, helping us to understand how the earth was formed and how things work. So although the concepts developed between the 1800s and the 1900s, incorporated some of the quantitative measurements that we also use today. Much of them were based on qualitative theories of how things work in combination with definitive and circumstantial evidence. So I think much of the change happened between the 1960s and 80s, where we had a major shift towards quantitative geology in a form of mathematical geology that took center stage. And this was mainly facilitated by a guy called Andrei Borisovich Vistelius. And around a similar period, though slightly earlier, because he started his work in the 1950s, another discipline leaning towards spatial statistics and geologic was born, and it became known as geostatistics, and it was led by our very own Daniel or Danny Krieg, and a French scientist known as Georges Francois Paul Marie Matheron. And from the above timeline, we can all agree that the modern geoscientist has a lot of concepts to deal with. And just to name a few, we're no longer only dealing with the rock types or few basic concepts, but we have to deal with complex system analysis, earth sciences, mathematical geology, science as a whole, theory, research in geoscience, and there's also education. And in the coming number of years, there will be more focus in time and space. So this begs a question to say that from 2020 onwards, what's next? What's going to be a new thing in geology? So before I say many things, I think it's good to actually keep up with the times. The graph that you see here is a Google Ngram showing how key phrases in geosciences have occurred in a corpus of books. From this, it is clear that certain disciplines in geology are being absorbed into other streams, and that we are in an era of geochemistry and machine learning. And if not handled properly, some of this discipline may lose value, as we have seen some recent closures and measures of geology departments, some of the European universities. So to start up my story, I would like to begin by showing you something that caught my eye, and it is one of came out this year. Not to say that the theme of my story has to do anything with the paper, but I think it is a good example to use for illustration. So geotheory has mainly reached now a mature state, as evident from the work that we tend to cite. Many people have worked in this field for quite some time. And to illustrate my point here, I'll use an example from the recent work that was done by Willem Kruger and his supervisor, Rais Letipov. I could have used any other example, but their diagrams have both the elements of classic and modern geology. And this actually enables us to see more into what we could not see before. So we often go to the field and make some field observations or take measurements. And with the observations, what we tend to do is to make some deductions based on what I call a single realization or a localized or observation, because it's difficult to cover the entire area. As you can see here, they have some samples that were taken in a particular locality. And this tend to be followed by a series of inductions. And by inductions, this is where people attempt to make some interpretations of complex systems from a single realization. So unless this is done by somebody who's quite skillful and objective, it can often lead to over or under interpretation of the system or how things work. So this methodology also naturally result in a lot of linear thinking if you're not skilled up, meaning it's difficult to even formulate a story from a single observation. So it requires you to have some sort of years of experience working in the field. And today's talk is going to try to make sure that even those who do not have much experience to analyze complex systems have an opportunity to start working on some of these systems. So with the advent of technology, geotheory and geologic, we now have an opportunity to increase our confidence on geological education and complex system analysis. And how do we do this? For the purpose of this talk, we'll discuss the aspects of machine learning, which is a branch of artificial intelligence, and it's also a branch of data science. And the two of them together are some of the main pillars of the fourth industrial revolution. So machine learning consists of several sub-disciplines, and within this sub-disciplines, we have supervised machine learning, unsupervised, and reinforcement learning. There are also other sub-disciplines that are not really machine learning, but people tend to associate them as part of machine learning, and this includes things such as deep learning. I'm not going to be covering any deep learning in this particular talk, so I will limit my activities on machine learning. What we also have as the modern geologist toolkit is that the second aspect, which I'm also going to cover in detail, is numerical simulation, mainly geostatistical components that deals with sequential Gaussian simulation in the context of this talk, but numerical simulations like fluid dynamics also exist in the broader scale of geosciences. So for the geophysicists who may be in the audience, this is another type of modeling or inverse modeling, but mainly dealing with more on the geostatistical inversion, which is based on geological information that includes seismic data, diamond drilling data or drilling data, and core logging. The other thing that you should also notice is that it applies random function theory and geostatistics. So in geostatistics, we tend to deal with a lot of histograms, variograms, among other components, and we'll get an opportunity to actually get a slice of each and every one of these concepts. So in order to ensure that there is something that is sound that everyone takes home, I will be using or demonstrate the machine learning and inverse modeling in geostatistics by showcasing two case studies. The first case study is going to be dealing with a gold deposit from the Wits Basin, which is where I have worked extensively. And the second one is going to be focusing on a hydrocarbon reservoir modeling from one of the South African coastlines, which I also did some consulting work on. So for both the case studies, I will not disclose the exact location due to confidentiality agreements that I have signed with the people who have given me data. I'll also want to put a short disclaimer quickly. So in order to minimize the use of commercial software, 90% of the models that you are going to see today are based on open source Python code called Geostats with GSLib. It is a geostatistical library developed by Clayton Dodge and John L in 1988. So the Python workflow and the source code itself was written by Michael Patch, who is an associate professor at University of Texas in Austin. So GeostatLib with GSLib, a set of machine learning algorithms that were developed by myself and Steven Zhang, known as GSPRED, were utilized extensively. And then on the resource classification and Monte Carlo simulation, this is based on a code that was developed by Leon Tolmay and myself, and all the work belongs to Tolmay Enterprises. The other thing that you should also be aware of is that there will be some of the images that were given to me by a guy called Daniel Mikes, who used to be based here in South Africa, but is back in the Netherlands. He provided permission for me to use some of his data for modeling. So let's start with the first case study. In the first case study, I'm dealing with a gold deposit. So just to give you some brief introduction, sequential Gaussian simulation is a procedure that uses the Kriging mean and variance to generate a Gaussian field of some kind, which is used to model the observed data. It is different from forward modeling that people are used to, in that a grid or model is constructed from the data itself. So sequential Gaussian simulation constructs an artificial data that satisfies some notion of realism compared to the real data. And it is most commonly used in geostatistical reservoir modeling and also for some complex gold deposits. So in the hydrocarbon side, people tend to use this to analyze continuous variables such as porosity. It allows us to examine different possibilities that are not well sampled by initial real data itself, and basically creates a large amount of potential conjectures of the underlying system. Each and every one of them produce some sort of sufficient similar, and if they are not similar, they need to be assessed further. So they have to satisfy some sort of a Kriging mean and variance equality at the end. So to give you an example of why this is quite useful, imagine that there is a disease spreading somewhere in a community, as we're currently facing at the moment, and we only have spatial data of few sick individuals, and we can try to construct some sort of various spatial scenarios of who transmitted to whom, and that will give us some sort of first educated guess of where the infection or the virus started from. But however, for case study number one, the diagram that you see here illustrates the procedure that needs to be followed to generate the simulation. The process begins, as you can see from the top blue colors there, it begins with going into the field where you do a lot of sampling, or you collect a number of samples in some sort of a control grid of some kind, followed by debiasing the samples, because most of the time we introduce some biasness when we take samples, because we either sample preferential areas or we do random sampling. So we also have to do some outlier treatments that may be obtained, and then create a Gaussian field using a normal score transformation. And after attaining a Gaussian anamorphosis, we must use this data to actually create multiple realization, which later assist us to understand complex system based on multiple equiprobable uncertainties, which is to say, in simplification, that to within a very small area that we may have sampled, we may get more multiple scenarios that are going to guide us on whether whatever we're seeing represent or can be generalized over areas that were not fully sampled. So to start with this, here's an example of a sample grade of some kind, showing a location of samples and a goal grade in the scale bar, as you can see. These samples will have gone through a standard QA/QC that is conducted. Most of the time, it's either the exploration geologist. The lab also does a lot of QA/QC checks, and then the resource geologists, before they utilize the data, they also do QA/QC on the data. But one thing that you need to be aware of is that machine learning offers an additional layer of QA/QC, which was not possible before. And I will demonstrate that in the next slide. And what I mean by this is that this new layer, which is brought by machine learning, could be done using what we call network analysis, which basically examines complex relationship within data and can easily spot a multidimensional outlier or a new anomaly in the data, meaning it automatically detects any anomalies that you may have in your data set. And to illustrate my point, consider again the current challenge that we're facing with COVID-19 pandemic. So let us consider that we have a network comprising of different airports across the world. We can find that airports having greater number of connections and identify them as the hotspots. Then what we simply do is spreading the strength of a disease can be visualized as a linkage strength between various nodes, which depicts the hotspots. Then we can quickly observe which hotspots are spreading to other hotspots and to see their correlation for us to take some sort of a corrective action. The same can be applied with geoscientific samples, because each and every sample is visualized by a point or a node, as you can see in the diagram. Its connection shows the affinity to various features. If we're dealing with a Wits gold, it means we're referring to things such as sedimentological characteristics that may include pebble size or geochemical data of some kind where we have analyzed a number of elements. And this will form some sort of a cluster bonded together by the links. So with stronger linkages, what we simply have is that they form some sort of gravity clusters. They do this by depicting the attraction between the nodes as a force similar to gravity between planets. So this automates outlier detection while providing spatially constrained clusters on a large data set. So most of the time, whenever you're dealing with large data set in the resource side of things, you also want to see if there's any clusters of some kind or there's some sort of geodomains. So this now can easily be depicted automatically, as you can see from the diagram that you see here, and outliers also can be screened out speedily. In one of our recent work, we have also used machine learning to actually substitute the bulk amount of chemical assays that are utilized or that are taken whenever people are mining gold deposits. And what we simply did in here was to utilize the power of geology that is being collected on a daily basis by the mine geologists. This includes underground mappings. This also includes some historic assay data. So we built an algorithm that can actually automatically depict and tell you how much off it is from predicting point values, and it works quite well also with block models, as will be demonstrated as part of this sequential Gaussian simulation. So most often, special locations of geological samples are randomly or regularly sampled, meaning that there is preferential sampling which introduces some sort of a bias. And in order to deal with this, there are a number of things that needs to be done. The first thing that we need to do is to plot our samples in some sort of a grid where we have taken samples. So one of the important parts of sequential Gaussian simulation is determining the appropriate block size that we are going to be creating, or the so-called cell size or grid size. So to overcome this, there is something that needs to be done. We use sample declustering algorithms, which remove sampling density bias. So imagine that we have sampled a hand sample of the Orange Basin, to give an example, and try to use it to generalize some theory on the entire Orange Basin by only taking few samples, and to other systems too. So most of the time, this will not be a good scientific inquiry because we don't have sufficient samples, or we have only sampled preferentially specific portions of the grid. So the figures that you see in the left-hand side here shows the different cell sizes which contain samples in some sort of a grid. What you see in figure 1 is that we can observe a well-pronounced clustering in the top left, in the top left-hand corner, with the result that this area receives majority of the weight if you were to do some sort of estimation or simulation. So the information presented by denser sampled area may reveal some sort of an anomaly which we don't see in the sparsely sampled areas due to sampling bias. So if we look at figure 2, again on the left-hand side, and this is the top left-hand side cluster, is evident that in 5 of the blocks, and as such, there is some sort of clustering that carries a weight of about 45%. And this again will result in some sort of biasness if we're to use that as our grid size of position of our cells. In the third figure that you see in there, the cluster is found in 4 blocks, an improvement, but still significantly overrepresentation of the distribution of a sample in a particular block. Figure 4 indicates the idealized situation, with the cluster being approximately equal to its area that it represents, as well as having the majority of the blocks represented with some sort of a data. So in figure 5, one observed the top left, in the top left hand, again, is now once again receiving increasing amount of weight, and therefore over-representing the mean that we may get from the overall data because of over-weighting. So finally, in figure 6, it indicates that the block size of the area of interest with results to the mean becomes again the similar data that we see in figure 1. So from the above, it is easy to deduce that in any declustering exercise, one will start with an unclustered mean, as we have seen in figure 1, but you'll also end with an unclustered mean, meaning it's key to know which point actually you are going to decide to pick your cell size. So this in turn requires some sort of a mathematical translation, which can be solved easily using the first derivative. So what you see on the right-hand side and the lower figures is what we call declustering mean samples that are based on quadratic form of some kind. So what it does is it gives us an optimal declustering position, and this in turn can be obtained by simply using a first derivative. So where you see I have marked with some sort of a greenish line or a black line that goes vertically on the lower portion, this was done by fitting the least square function, and this provide an area or a region where we can find an appropriate cell size. And this, in this case, as I have mentioned, there is only one idealized figure. The next thing that you have to do is that when we have fulfilled the grid size requirement and we have de-biased the samples to make sure that there is no bias, we have to transform the data into some sort of normality, or to attain a Gaussian field. And we do this using normal score transformation. This will actually change our data from whatever mean that it will be having to a mean of 0 and a unity variance, meaning a variance of 1. This is convenient because now a plethora of methods intended for unit normal data can be applied to the transformed data. The next thing that we have to do, most geostatisticians will be quite aware of this, because it's one of the things that you have to do as part of geostats practitioners. So it is also one of the most exciting stages of sequential Gaussian simulation, and it involves Variogram modeling. So similar to simple and ordinary kriging processes that people tend to use, we use variograms to assess the variability between data points as a function of distance. So the first thing that we have to do is to calculate what is known as the experimental variogram and plot var maps, which is the left-hand side map that you see in there. The var map provide a visual inspection of spatial continuity. So the bluish colors that you see in this var map shows directions of areas of low variability, while the higher order colors, such as the reddish and yellowish colors, show directions or areas where we have high variability. This enables us to see areas of major horizontal continuity and some sort of geometric and isotropy if it exists. So as for the experimental variogram, I have put some labels on the right-hand figure to help those who have never modeled one before with some interpretations. And what you will see in here is that modeling of the variogram is what people call geopoetry, because it requires some sort of careful examination of your data and spatial continuity. It also becomes more exciting when you try to fit a model of some kind in 3 dimensions. And in the next slide, I will show you some of the things to do with variogram modeling, which is this one. So here we start fitting a model into an experimental variogram. Because the simulation algorithm requires some sort of a positive definite model of spatial variability, the experimental variogram cannot be used directly. So instead, a model must be fitted to the data to approximately describe the spatial continuity of the data itself. If you don't get what this means, it's not a big deal for now, but you will see how this plays out when you start now with the simulations. So in most cases, for this type of the ore deposits, such as the Wits type ore deposits, a spherical model tends to fit the data. This model basically says that there is some correlation between samples, and it weakens to no correlation beyond some sort of a distance, like a sphere of influence. One thing that you should also be aware of, Michael Patch's Webflow has a very nice tool which is an interactive variogram model that allows you to fit a live variogram model, and you can change the parameters what you see. And in addition to this, he also put in some sort of an interpolation tool that can interpolate any other azimuth directions that are possible. And in our GS spread formulation, we have an auto model fitting parameter or routine for isotropic variogram, and this is based in the most applicable or highly precise mathematical approximation, which enables users to get the best spatial continuity constraints. This just means that we can fit a variogram to the best of what we can do without much of human intervention by just using functions that are embedded into it. So once we have our data transformed, debiased, and so forth, in addition to modeling spatial correlation, direct and causal relationship between the data that you are looking for needs to be assessed. In this example, many people have tried to plot channel width versus gold grades and found that there is no relationship at all. But what we have found is that in some of the localities or in some of the reefs, when you use normal score transformation, which is an example here that you see on the far right-hand side. So in this example, you'll notice that there is some sort of a direct proportional positive relationship between gold content or gold grade and channel width. The channel width is the thickness of the gold-bearing reefs for those who may ask, so it refers to more of the thickness than the width itself. So such relationship that we notice here in the channel width and the gold grade is very useful when considering to do things such as multivariate simulations or predictions or co-located simulation, as will be demonstrated later as part of this presentation. So now let's look into something. Now the most exciting part is the simulation, which is what we are looking at in here. So from that grade that you have seen, we have actually produced some sort of simulation, this process can use a number of algorithms. The most common algorithms that people use is the simple kriging and ordinary kriging algorithms. And this has actually worked quite well, not only for simulation, but for interpolation or estimation of the grade of this type of ore deposits. So to do this, you need to generate a random path through the grid node that I have showed you before, and then visit a node in the random path and use kriging to estimate a mean and standard deviation at a node based on the surrounding data and variogram that we were modeling. Then generate a local conditional probability of distribution for each and every locality. I have purposefully highlighted a red box in the simple and ordinary kriging simulations that you can see on the left-hand side. This is an area that has no samples at all, but it shows a high-grade stochastic island of some kind. This kind of anomaly is quite interesting, but how realistic is it? And that's the question that people need to ask whenever you find anomalies in places that you don't even have samples. So given it has no real supporting samples, if you recall from the example that I have given on deduction and induction when I started using a single realization, this is exactly that. If you only use one realization, you will assume that this stochastic island represents an area of high-grade offshoot. But one could be well wrong actually in this, because this may be an artifact of either the simulation algorithm, or it means there is some sort of an over assumption in the processes that you are using. But if I do simulations 1,000 times without adding samples in that particular area, and consistently we observe the occurrence of this gold-rich island, it could be an area indicating that it needs to be explored further for resource potential. Or otherwise, if we don't observe it often again, it simply means that it's an area that needs to be treated otherwise, because it may lead to over or under interpretation, or under or over estimation of those particular reasons. So this is key, that you need some sort of a simulation in a number of areas that is more realistic for you to be able to have a quantitative measure or a quantitative conjecture of what you are looking at. And to do this, in this particular slide, what I have shown in here is about 4 realization of the same field. So it means I have just applied realization using the same grade, but simulated a number of times. Usually I do about 50 to 200 simulations. And here I just taken 4 slides of the simulation. So a random simulation path was used to avoid the artifacts induced by visiting grid nodes in a regular fashion. The random path must go through each cell once and in a random order. This result possibly gives a better representation of the natural variability of the property that is under consideration of being measured, and it provides a means of quantifying uncertainty where you can actually give interpretation that are based on sound and quantitative ground for the validity of our model. Imagine that we could say that hypothesis X is likely to be correct with the context of our data at a probability of 75%, and the hypothesis Y is evaluated at 80%. Then you have a real shot to discriminate the validity of various hypotheses, not only basing it on a single realization. So in this slide, we see a combination of all realizations. So it means those 200 or 1,000 realizations have been combined together to produce the final model on the left-hand side. So with this model, we have known confidence level per sample point, and also at the block level, because each and every block has been simulated a number of times, and the uncertainty of that particular block has been quantified. In addition, as I have mentioned, that sometimes it's key to know the relationship between the different variables. The relationship can be causal or direct, or it may be related to the mode of geological processes that we have modeled between gold grade and channel width. But these can assist us to use that relationship to simulate things such as channel width that also add value in our modeling process. So we can use some sort of a co-located, co-kriging algorithm to produce a nice quantitative channel width model on the right-hand side by simply observing such a relationship. But whenever you have some sort of simulations, sequential Gaussian simulation model outputs must always be validated to ensure that we are not relying on over or under realizations. There are several ways to do post-simulation validation, and each cross-validation methodology adds confidence to our simulation. So the validation methods that are available or that many people use, or that I have been using myself, include the following. I'll just list a few of them. The first one is more of comparing the so-called ergodic and non-ergodic variograms with declustering, normal score transformation, and cumulative distribution functions. And these lines that you see, the blue lines that you see on the variogram here, this is what we call ergodic variograms or non-ergodic variograms, and I will tell you the difference now. You can also produce a number of other models by comparing the mean and the variance of the total realization with the values that you got from the declustered grade or ordinary kriging and simple kriging estimations. Again, you can do more post-simulation models, which include an E-type, which is a local conditional expectation and conditional variance. So the other thing that you should also pay attention to, this ergodic and non-ergodic states are concepts that have been borrowed from physics. So they were initially formulated by a guy called Ludwig Edward Boltzmann, an Australian physicist who had a very good inclination for spatial statistics or statistics itself, and was the founding father for statistical physics that many people practice today, upon which we rely for things such as phase diagrams in geology, the theoretical underpinnings of the popular AlphaMath software that people use to model a number of geological events. So I come from both the fields of science and engineering, and with this we have always been taught in some of the lessons that Boltzmann's ergodic hypothesis is that if I draw any random sample in the field that I have been studying, the values of that particular field should some sort of remain constant or similar. And when the value starts changing, it implies that we have a non-ergodic system. A practical way to actually look into this is to actually toss a coin of some kind. So it means I can toss 1,000 coins and toss them 10,000 times. So I can toss a single coin 10,000 times. It will yield exactly the same statistics. So that hypothesis is actually applied also in simulations where we look at, are we going to get similar conditional expectations or there will be high variability? So a system that is going to be more stationary will be referred to as ergodic, and the one that is more variable will actually be referred to as non-ergodic, just to simplify it. At this point, I think I would like to take a detour before we do the second case study. And here we're going to look at what does all that I have covered so far mean? Can this be applied anywhere in the industry, or is just an academic exercise that I did? So to do this, we have an organization which is called CRISCO, or the Committee for Mineral Reserves, International Reporting Standards. The mission of CRISCO is to contribute to earnings and maintaining the trust by promoting high standards of reporting mineral resources estimates. So under CRISCO, we have a number of member organizations, and some of these member organizations includes our own SAMRE code, or the South African code for the reporting of exploration results, mineral resources, and mineral reserves. And within the SAMRE code, mining companies are required to declare their exploration results. They also required to declare mineral resources and mineral reserves using specific categories that are actually guided by these same codes. So in the interest of time, I will not explain each and every one of these codes. I think the Geological Society is running a workshop, or will be running a workshop on this, or you can also visit their website. They do explain this in detail. So sequential Gaussian simulation and machine learning plays a critical role in adding more confidence to fulfill some of the CRISCO requirements. So I will provide some application examples in the next slide to illustrate the usefulness of what we have done to show that it does not only end in research. So what you are looking at here is a real-life example for operating mines where we undertook mineral resources estimation and used simulation results to create resource classification categories. So we have also assessed the project feasibility by determining factors such as the asset's net present value, which is a common financial indicator of a commercial enterprise, and the profit margin over a range of cut-off grade. Those who are working in the field have seen many of these curves. So the idea here is that strategic planning is led by financial outcomes, and it is tactically expressed in the process, such as how a mine is planned to maximize the NPV or some other indicators, bearing in mind the nature of the ore body, the grades that are found in there. That's why you have to work in a range of cut-off grades. So in this diagram of the NPV, we can see that the NPV is not just a linear function of the panel grade that you can simply calculate, which is the ore grade of the extracted panel. Therefore, if we use the NPV as the indicator of strategic planning, as one example, we can identify an average target panel grade that is more optimal, bearing in mind that the fact that you have optimal NPV does not equate to you having optimum profit margin. So most of the time you have to make a decision between the two. Another application is where we have used simulation in combination with machine learning to produce the best approximation of the grade tonnage curve that you see on the top right. And here, in this example, many simulations are used to understand the range of the cut-off grades, again in detail, that results in financial viability of a particular company. We can look at optimistic scenarios and pessimistic scenarios to get a complete sense of probable outcomes. And with this, you can also it can also assist you to frame the actual outcome against the expectation to understand the performance and the resource model viability or reliability. The other thing that you can use simulations in this type of deposit, it's more of reliable grade control models. You can also use it to guide your exploration drilling, either for grade control or near mine exploration, which is guided by the use of conditional simulation and machine learning. With this, I would like to get back again to the presentation by now looking at our second case study. So we are now dealing with our second case study, which will be shorter since I'm sure I'm starting to run out of time. So this slide here shows two probable procedures that can be followed for hydrocarbon reservoir modeling. Again, it starts with going into the field, collect some data, and it ends with some sort of an equiprobable model that either boosts your confidence on what you are exploring for or what you are modeling. And again, the idea here is to mitigate against interpretation bias by looking at a variety of models. But unlike in the ore case study that I have presented of gold, for hydrocarbon reservoir modeling, we can also use an additional component, which is the Markov chain Monte Carlo simulation, or what is known as MCMC methods, which comprises a class of algorithms for sampling from a probability distribution of some kind to explore potential outcomes that we are looking for whenever we explore for hydrocarbons. It is a way actually to probe the reaction of a system using random inputs and observing correlation between inputs and outcomes simultaneously. So to do this, I did a lot of sedimentology in my undergrad years and my honors years. So like any Earth system, we need to do a number of things before we can jump into simulations. One of the key things that we need to do in hydrocarbon reservoir modeling that we have to do is mainly basin analysis and to do trajectory studies. So this involves understanding the stratotypes, things such as sea level changes and complex system behavior, because we need to ensure that we are looking for the right targets and we are looking at the right sediments or the right rock or the right basin. So we also need to know the dynamics that govern in-phase cycles. And by in-phase cycles, I mean that the sea level and supply are in phase, meaning that the sea level high corresponds to supply maximum and vice versa. So when we have outphase, it means it's just the opposite of that. So another key thing that we need to know is the stratopatterns. And what we usually have is that whenever we do detailed sedimentological work in the basins that potentially host or are closer to hydrocarbons, we note certain things. To give you an example, we can observe things such as the tracers that I have marked in there. So tracers can tell us something about the temporary events that happen in that particular basin. We can also look at laminae, and laminae can also tell us something about the spatial events, which are key when it comes to estimation of any property that relates to hydrocarbon exploration. The other thing is we also look at truncation between different rocks, can be either be a shale and a sandstone of some kind, which tells us something about the strata events. Another thing that we also need to look, so there is a lot of preparation that we have to do when we're dealing with hydrocarbons. So one aspect that we need to look into is seismic data. So there is a lot of reflection seismic that needs to be looked into it. So we have to examine this in detail. So if we combine our field observations, some sort of geological interpretation with seismic data, we can produce the so-called seismostratigraphy. And a seismostratigraphy is quite useful in this regards because it explains a number of things. The first one is that the strata units that we tend to see tell us something about the sequences that we have in that basin. The other thing that you can also add in there is the strata surfaces, which tell us something about the sequence boundaries. And then we can also differentiate here between major boundaries versus minor boundaries. We can also check levels of transgressions or periods of regression. So from this data, we can now know regions that represent things such as flooding events or erosion surfaces or any post-depositional overprints that may have affected the distribution or the preservation of our hydrocarbons. So once we have satisfied with our field observations, including preliminary seismic interpretation, we can start some sort of a drilling campaign in a number of places. This was a well-drilled. Some of the time you don't find this cluster of boreholes because this is quite costly. So this will include taking a number of samples, analyzing them for multiple variables, simple ones that you can think of are parameters or properties such as porosity, permeability, the chemistry, the amount of potential of the gas that may be found in a particular place or hydrocarbons that may be in situ. But the challenge always comes in this type of field. We collect very large amount of data. So I'll give a simple example that everyone does whenever they're dealing with geochemistry, analyzing a number of major elements, of which some of them we just got used to analyzing them without using them or interpreting them for anything. So when we have all the data, we are now faced with the challenge of how best do we interpret and visualize multidimensional data. For an example, if we have analyzed samples for multiple elements, as you can see in this figure, how do we use the data to link with the field observations? If you attempt to do some standard geological matrix diagrams or ternaries or any other standard 2D plots, excuse me, you will hardly see any distinction between the different samples. It's even worse when you are looking at shale samples, as they are quite not easy or they are difficult to discriminate visually when they are coming from a similar sequence. So normally we'll have to do some sort of a handcraft interaction, looking at things such as elemental ratios and try to normalize them. And our ability to discover insights is basically predicated because our intuition. So we'll try to analyze our data based on our own understanding without now visualizing all elements. So we'll pick certain elements that make sense to us and ignore the others. So this is a more of a hypothesis-driven scientific inquiry. And we can also use data-driven scientific methods of some kind, if that is the question. So this is what underpins many of the fields that are known that ends with an omics of some kind, like genomics. And I'll demonstrate this in the next number of slides. So faced with a large amount of data, we have to turn into machine learning as a place where we can start and seek the help of cluster analysis. And one such method in cluster analysis is hierarchical clustering. This allows you to select from many possible hierarchical algorithms, and the intuition of crafting interaction in terms has changed from selectively picking elements to looking at an algorithm that best represent or visualize your data. So in this example, we have used the agglomerative hierarchical clustering algorithm, and its results can be visualized in a cluster hierarchy that is commonly displayed as a tree diagram called the dendrogram. Those who have worked a lot with XRMDs and so forth, you will notice that when you do some quantification of some kind, you can also produce a dendrogram. With machine learning, you can actually do this with your trace elements without knowing the crystal faces of the material that you are looking at. So the algorithm begins by placing each sample in a separate cluster. Then at each step, two clusters that are most similar according to a specific definition of similarity that it picks up in the data are joined into a single new cluster. So once fused, objects are never separated. And you can see here now, we can start visualizing the clusters quite well. Second thing that you do in the discipline of genomics, which is the branch of molecular biology, and is concerned mainly with the structure of functions, evolution, and mapping of genomes, they use a combination of dendrograms and heat maps to visualize multidimensional data. In geology, we do use a lot of contour line maps and so forth, so we can actually apply this. So we have used the same analogy here in this example to classify shales based on their chemistry, similar to a contour plot that we plot as a geologist, and a heat map, which is a two-way display of data metrics in which individual cells that you see there are displayed as colored rectangles. So the color of a cell is shaded along a color gradient, and here warmer colors show more similarities between different samples, which are shown as rows in the matrix. So what you see at the x-axis of this diagram, or at the bottom, it's mainly element or oxide names. So it's starting with MgO, going to a number of things. You can also look at things such as carbonates and loss in ignition, among a number of things. So with this diagram, one can actually see more of a genetic patterns of the shales by only looking at the chemistry and tie it back from the observations that we had. And to further visualize this, you can use another diagram. So after you have achieved some sort of desirable clusters, what you need to do is to first now look at whether there is any chemical separation within the data or specific colors that stands up. And what we tend to do, we use the so-called parallel chemical coordinates. This is a system that in geology, when we're analyzing few samples, we call it spider diagrams of some kind, or multiple elements diagrams. So in machine learning, this falls under a group of parallel chemical coordinates, and this is where you can visualize more than thousands of the data sets based on the clusters. And once you have done this, you will notice that finally, this type of separation can be visualized now with our standard diagrams because we now have clusters. So machine learning has no problem with high dimensionality data. As you can see here, each of the clusters shown by a different color is unique in some sense, and that its chemical signature is not like those of the others. But this is not a simple binary divide across each element, which is why this is hard to do by hand. And lots of historic work has been put into developing interactions such as elemental ratios, whereas these techniques work well on huge data set to produce more generalizable knowledge, meaning once I get the signature of those particular shale, if I drill the next cycle, machine learning will be able to find out whether it's similar to what I have drilled before, or it's actually a new cluster that needs to be characterized. So if we're happy with that, from this point, we switch back again to conditional simulation and create some sort of probability maps of phases. An example is the probability map of sandstone versus shale that you see here, which is useful in reservoir characterization and exploration of hydrocarbons. And this can be easily discriminate between different phases. So you can see clearly your sand phases on the left-hand side, where you see their probability, which is marked by the red color. So the red color on the right-hand side shows that there is a clear definition between the other colors, which is bluish and greenish colors, and the red color. Whereas on the right-hand side, when you are looking at the shale, you can see that the probability of shale occurring where it used to be blue on the left-hand side when we're dealing with a limestone, with a sandstone, there is very nice boundaries that can be quite useful when it comes to simulation. So once you have fulfilled this, it means you can take your data again, take for your porosity and permeability or any other function. In the interest of time, I won't calculate any P10 or P90 in this, but it's a discussion that we can always have at some other time or in future geotalks. So again, we do multiple realizations similar to what we have done in a goal study, and we see if there is any correlation with the data. And with this, having decided which methodology we use, we can finally produce an equiprobable model of a hydrocarbon exploration site or well site, and use the relationship between porosity and permeability to co-simulate permeability. This will allow us to have a sense of potential locations of reservoirs, their sizes, and uncertainty associated with our interpretations. In the same sense, a reservoir that is not frequently seen in our simulation is probably not an exploration priority, meaning it's not something that you will decide to say, let me explore it while you have limited resources. So in this manner, we incorporate geological observations, measurements to support interpretations of the realizations and the uncertainties. This again puts realistic constraints on our model and avoid over-assumption of where we think there may be potential. So, what does all that I have presented so far mean, or what does all that I have covered in this geotalk mean? There are a number of points that we can take here. So here are a few of the points or benefits that both geotheory and geology can benefit from. The first one is more of rapid, accurate, in situ concentration prediction of metals, such as gold or PGEs, among a number of other metals. Then we can also get some high certainty on the ore reservoir characteristics because of these multiple equiprobable models. And then we also get to test hypothesis testing by quantitatively examining the prediction of the models. So multiple equiprobable visualizations of geological features can be done rapidly, and scale and variable reduction on a large data set can actually be used to enable sound interpretation. Other key thing that we can get is automated phases and geodomaining that we can get quickly. And then some deep insights into complex system that assist us to interpret things that we study to advance a particular theory. And lastly, this adds into the advancement of computational geosciences in line with the fourth industrial revolution. So to conclude, is that in 2003, Robert Frodeman wrote a book called Geology, where he was focusing on breaking the ground between philosophy and earth sciences. And a number of work has been done by Robert Frodeman and publications that were done by Daniel Mikes before. I think it's time that in our local context from our university, and not only our university, the industry as well, we move forward with a new concept where we advance this geologic by breaking the ground between spatial statistics, computational modeling, and earth sciences. And I would like to say thank you so much for joining us again for today's GeoTalk, and thanks for your time.
Thank you, Glenn. That is a really interesting, very complex, but really interesting topic. And I think judging by some of the questions we have, something that's very interesting to the audience. So keep your slides up there. And if you have some time, I'm going to pose some questions to you. Is that all right?
Oh, yes, that's all right.
Okay, so the first one comes from George. And George says, thanks, Glenn, for an interesting talk. With regards channel width and grade, what happens if you have a plot of grade only in grams per ton and a separate plot of channel width? If you plot the two plots side by side, would you expect to see a correlation? And then I'll let you answer that one, then there's a follow-up that I'll read out in a second.
Okay, so it will depend. At a local scale, you will be able to see some sort of correlation. So for an example, if my cell size or my block model is a 30 by 30 block model, within specific blocks, you will see some correlations, but within other blocks, or maybe the neighboring blocks, you may not see some correlation. So it's actually important to look at what sort of relationships are you looking for? Are you hoping to observe? Are you hoping to observe a global correlation between grade and channel width, as you have mentioned, or you are actually looking at a spatially constrained, localized correlations?
Okay, and then he follows up by saying, furthermore, if you now plot the gold accumulation in centimeters per grams per ton, how would you interpret any trends that you see? Would you expect the plot to resemble the grade only plot or the channel width only plot?
That is not something that you can easily tell. Let me just give you an example. You can have a grade of 2 grams per ton and a channel width of 100. It means your grade in CMGTs is going to be 200 CMGTs, but you only have 2 grams per ton. But at the same time, you can actually have a grade of 100 grams per ton and a channel width of 2 centimeters. So such a relationship, you first need to examine it to see if you are dealing with a system where a channel width is actually misleading you to think that you have a very good correlation between grade and channel width, only to find that it is merely a channel width influencing that. And that tends to happen a lot where we have multiple reefs stacked together. Can give an example with things such as that I have worked on before, the Middelflay Reef or the Black Reef, and in the West Rand Goldfields, the Kloof Reefs, where you do have these multiple layers of the reefs. And with this, if you're not careful enough, you will find yourself thinking that what you are having mainly represent the gold in grams per ton or CMGT. So I think context matters there. You need to understand your geology first.
Okay, super. And then we have a question from Masi. Would this simulation be reliable in assessing grade variability of ore in dumps, particularly old dumps, which have limited drilling information?
So the challenge of mine dumps is a bit complex. Of course, you can do conditional simulations in most of these tailings. We have done it on one. It didn't perform as much as we want because the entire dump, it was occupying an area of almost 8 hectares, and there was something like 12 boreholes that were drilled in there. Of course, the values that we got there were not quite nice, but within the areas where we had some sort of influence, I'm talking about areas where we have drilled these boreholes, there were some certainty, but to extrapolate it in the entire dump, you need to make sure that each and every variation in the dump has been sampled one way or the other. For an example, you can't just drill only on the top. You also have to have some boreholes on the edges of the dump for you to get a proper volume. So the simulation that one can do there, instead of relying on 2D slices, you can actually do a nice 3D volume reconstruction, and you do simulation per slices or per depth based on the height of the dump itself. So it can be done, but it requires additional things. And with limited samples, sometimes the certainty that you can get is very close to where you have your samples.
Great. And then the last question that we have, of course, you feel free, anyone, to ask any other additional questions whilst Glenn's dealing with this last one. This one is from Elton, who says, for hierarchical clustering, which characteristics are you using to cluster the samples together?
Okay, so I'll use a simple example that we will all understand from the geology side. So if I'm looking at shales, we tend to study shales for their provenance and so forth in many of the areas, be it Archean shales or Phanerozoic shales or anything like that. And what people tend to do is that if you have a high nickel content, as an example, they tend to say that most likely this was sourced from a mafic or an ultramafic rock of some kind. And if you have things such as elements that tend to be associated with felsic rocks, it means the provenance is going to be interpreted leaning into that. So with the hierarchical clustering, what the algorithm looks for, it looks for elements that tend to relate together either because they are higher compared to other elements in there. So instead of constructing a ratio of 2 elements, you're actually doing a ratio of multiple elements. So it's looking at the behavior of those elements that you have analyzed to create some sort of a signature to say that this type of shale are mainly rich in magnesium and nickel and so forth. So you don't actually tell it to say that nickel comes from an igneous rock or come from an igneous mineral or anything like that. It actually picks up based on the concentration that your samples have.
Okay, thanks. That's fantastic, Glenn. I think you've dealt with all the questions. I don't see any more questions popping up. So at that point, I'll just thank you once again for a really excellent talk. And I think it has many applications, especially going into the future, as you've shown, many different things. So I think this is very important, and I hope lots of students out there are watching, because these are things that we need to start to integrate more into our teaching. So to end off, let's just thank John Hancock from CCIC Coal for sponsoring these talks. And of course, a very important part of our Geotalks is some form of social interaction. And of course, we can't get that in person. So in the Q&A bar, you will see a link to a Zoom meeting where we can have some virtual networking after this for 30 minutes or so, or for as long as you like. And so you'll see the meeting code there and the passcode. And if Glenn has some time, I'm sure he'll join us, but I'll certainly be there and we can catch up with whoever would like to join. And the last housekeeping that I should do is just to share the talks for the next 2 weeks. And so as you'll see up on the screen right now, we have a talk next week by Michael Westgate, which is about legacy seismic data, the past informing the present. And the week after that, we have a talk all the way from Eastern Australia by Tara Dokic, very different this time, about early signs of life in hot spring deposits from the Pilbara, implications for astrobiology. And please note for that talk is going to be at 12 o'clock, so that Tara doesn't have to be up at 1 a.m. In her morning. We'll have that talk live at 12 o'clock from Eastern Australia, from Sydney, and then we'll rebroadcast the recording at 4:30. So you'll have 2 options for watching that talk. All right, thanks everyone. And if you are interested, we will see you on the Zoom session shortly. Thanks again, Glenn.